Okay, so before we get to the most rigorous proof of the time complexity of the average case of the quicksort, let's do a very quick review on what we have already know. Well, for the quicksort, so what's the worst case? The worst case is we have the pivot, and then all the remaining of the values are on one side. So the pivot is here, and then we have 0 to n minus 1 partition. That's the worst. And if we keep on doing this from the very beginning to the very end, and then we have the worst case scenario. In this case, we are gonna this is not divide and conquer, because every time we only have one value sorted at the right place, and for the rest of them we still have to sort them because they're all on the other side. And so we have the tn as the tn n minus 1 and plus the theta n. So this is not divide and conquer, this is more at the getting one step closer process. So this will work out as a theta n square. And for the best case, we always have the 50% to 50% partition, and this is the best case. And we are if we keep on doing that, and we will have the tn equals 2 t n divided by 2 and plus the theta n, and this will work out to be a theta n log n. So that's the best case. And well, and then we move on and we analyze the case that this is definitely bad, but not the worst. And that is we have 90% on one side and then 10% on the other side. And for the partition, and we still have a n here, and which I'm just using the n instead of the on to make it a little bit easier. And then we can prove that it's even though we have the 90% to 10% constantly, it is still a n log n time, right? And then for even worse, 99% versus 1%, it is still a n log n time. And then our feeling is, well, except the worst case, which is nothing to n minus 1 partition. It doesn't matter it is 10% to 90% or it is 1% to 99%. Those cases will all be n log n. And for the average case, it can't be as bad as that. So our feeling is for the average case, it still gotta be a somewhere at a n log n algorithm for the quicksort. Okay, but we still have to do a formal proof. And for the formal proof of the average case, and we know we are going to have a mix of the bad partitions versus the good partitions. And for what is bad and what is good? Well, and remember, for all the possible splits, when we have n values, the partition could go anywhere between 0 to n minus 1 to n minus 1 versus 0. And the reason is, well, you have 0 on one side and n minus 1 on the other side is for the partition. We don't want to cut the pivot, because the pivot will stay there, and once we have the pivot put at the right place, and then the pivot won't be sorted again, right? So if other than the pivot, we have some value on one side and some value on the other side. But if you want to add those two parts of the values together and we exclude the pivot, the sum of the values on both two parts will be n minus 1. So for the n minus 1 values, it could be 0 to n minus 1, or 1 to n minus 2, or 2 to n minus 3, etc. So those are all the possible partitions. And what's the probability of each possible partition? And the answer will be 1 divided by n, because the chances of having different partitions of the given n values will be equal to each other. And then if we want to add all the possible costs of all the possible partitions together, and then we have to have a summation or the sigma in our Tn. That is, well, for any k value between 0 to n minus 1, and we are going to have the tk to t n minus 1 minus k together, and then we have to put a sigma because k could be any value between 0 to n minus 1, and then the probability will be 1 divided by n. And remember, for the partition, the cost will be a theta n. And then we want to massage this a little bit, and we want to extract the 2 here because for each of the tk, we are going to count that twice. So we want to extract the 2 here. So this summation or the sigma will be easier. Okay, so this is the Tn using the possibility of all the possible partitions. Okay, and then we had this discussion. Well, we want to get the answer, and the answer is already, we have already talked about that. And considering the 99 to 1 or 1 to 9 partition, and then well, we feel that for the average case, the Tn will be O n log n. And after that, what's the inductive hypothesis? We want to assume that, well, for the Tn will be smaller or equal to A log n, A n log n plus B for some of the constant value of A and B. And then what substitution we want to do? We want to assume that for any k value and in the recursion, and this Tn or this Tk will hold. And eventually we want to prove that it is true for the entire Tn. So let's jump into the really painful mathematical proof of this class. Okay, so we started from here, and then this is the recursion we want to solve, and then we want to substitute this tk because for any of the possible tk, and we assume that, well, this tk will be smaller or equal to ak log k plus b. So this is the first part, and we plug in the inductive hypothesis. And after that, what are we doing here? Well, we are trying to get rid of the k equals 0 case, because you see this sigma, we start from the 0, and now we have the sigma starting k from 1. Why? Because when we have the k at 0, and then this term will be 0, so that is actually a b itself. So we want to extract that b out, and that b is for k equals 0. Okay, so, and then what do we do in the next step? So for the next step, we are taking this b out, and then this b will become this term. Okay, so, and then we got this part. And what in the next step? We find that this 2b divided by n is gone. Why? Because we have a theta n. Theta n is linear. And if we put 2b divided by n, and this term is not as significant as the theta n, so this is not a significant part. So you can say it is fold into the theta n, or you can say it is absorbed by the theta n. So we get rid of this part. Okay, so it is still complicated. So this is a new recursion to be solved. And what do we do in the next part? Okay, we are trying to break the left part and the right part, which is the b. So we are breaking this sigma into 2 smaller sigmas. Okay, and after that, let's work on the smaller part, which is the 2n, and then sigma from k from 1 to n minus 1 b. Okay, what's the problem? Then you can see after the sigma, there's no there's no k at all. So there are just a total of n minus 1 b's adding together. So after having that, and then how about we just adding n minus 1 of the b's together? So n minus 1, and then multiplied by 2b divided by n. Okay, so what are we doing in the next step? Okay, well, for the n minus 1, and then divided by n, and this term will always be smaller than 1. So 2b divided by n and multiplied by n minus 1 will always be smaller or equal to 2b. So we don't have to really worry about this n minus 1 and divided by this n here. So we get rid of them to make our case even easier. So we get rid of this this n minus 1 minus divided by n. So we make this case even easier. And this part, so the sum from of k log k from k equals 1 to n minus 1, this is a very big part we want to solve. But well, we are going to have a couple more slides, and before we move on, let me just jump in and then give you the solution. So we just plug in the sum of this in I just plug in this this summation, the result of this summation as this, okay? And then how do we prove that? Later we are going to have another set of the slides. And then, okay, let's move on. And after that, and I want to move the 2a divided by n into those two parts inside of the parentheses, and then we have this part, and eventually we have the a n log n, and then plus a b, and then we plus a few more things, so we can prove that for this tn, it is smaller or equal to a n log n and then plus b. And then for this part, well, we have something additional, but for whatever in this parenthesis, that is linear, right? That is linear to n. By observing that it is linear to n, and we know it can be absorbed by this a n log n, because n log n grows faster than linear, so whatever in the parentheses can be absorbed by the a n log n. So eventually we are able to prove that for the tn, it has an upper bound of a n log n plus b. What does that mean? This means, well, this is a n log n algorithm, right? So it seems our work is done. We have proven that for when we consider all the possible partitions from 0 to n minus 1 and all the way down to n minus 1 versus 0, for all the possible partitions considered and using the probability, and then the tn for average case of the quicksort, it is still smaller or equal to a n log n plus b. So that is a O n log n algorithm. So are we finished? No, there is still one part we haven't done yet. So we want to figure out this summation. That is k log k for all the possible values of the k from the 1 to n minus 1. And the trick I'm doing here is, well, for the range between 1 to n minus 1. I'm breaking that into two parts. For the first part, I'm doing from k equals 1 to the half n. And then the second one, I do the half n to n minus 1. Okay, so I'm breaking it to two halves to make our life easier. And then let's move on and see how we can solve that. So what are we doing in the next line? So for the next line, I'm substituting the upper half, and then instead of doing the log k, now I'm doing the log n. So for the log n, it doesn't really have the k inside this log n part, so I want to extract the log n outside of this summation. So this log n will be extracted outside. So ta-da, we got the summation a little bit smaller, so hopefully that's easier. Okay, so this is the summation we want to solve, and how do we do that? And okay, and how about we work on the left side for now? So instead of this log k, and remember we are doing this summation from k from 1 all the way up to half n. So instead of doing the log k here, how about I do the half n, log half n? So, and again for the log half n, and for the log half n, since we get rid of the k value, and then we can do log n divided by 2 equals log n minus 1. So let's substitute this log n divided by 2 to log n minus 1. And then we want to, what are we doing here? We are moving the log n minus 1 outside of this summation. So okay, so for both of the summation, actually they are getting a little bit smaller. So this is what we want to have. And after that, this is summation we want to solve. And after that, we want to multiply the first summation into the two terms inside the parentheses. So we got this one. So even though it's getting a little bit complicated, and don't worry about that, the things will get easier again. So what are we doing here? So for this part, we are combining two of the summations. So for the first summation and the last summation, the first summation is from k from 1 to half n minus 1, and then on the last summation it is from the half n to the half n to n minus 1. So for the first and the last summation, they can be combined together. Okay, so let's go ahead and do that. And after that, you have a summation of the k from 1 to n minus 1. And how can we do that? That is the Gaussian series, right? That's a sequence of the natural numbers from 1, 2, 3, and all the way up to n minus 1. And what's the sum? The sum will be n minus 1 and multiplied by n and divided by 2. So that's Gaussian series. Okay, and then and then we just massage this massage the first term a little bit, and after that we want to work on the second summation. For the second summation, you can see this is another Gaussian series, but for that Gaussian series, that is from 1 to n minus n divided by 2 minus 1. But anyhow, this is another Gaussian, and then we can apply the Gaussian series again, and after that we just touch this equation a little bit more, and then we got this. Okay, so eventually we are able to prove that for the sum of the k log k for all the k values from 1 up to n minus 1, and it is greater than this part. And this is a part we plug in into our formal proof earlier. Okay, so now our work is really done, and I know this is painful, and if you're still watching this video from all the way down here, congratulations, you're done. Okay, and this is probably the hardest, the most mathematical proof of this course. Okay, congratulations, you have finished. And for the reading part, and remember, now you can move on and read the section 7.4 of our textbook. Okay, so that's it for today, and I will oh, and by the way, and the midterm will be well, in the next class there won't be the new course videos because we are doing a exam. Okay, so good luck. Bye.